You could have an infinite sum, like a sum of infinite numbers, and it'll lead you to a finite number, and that the limit is that number that we approach. We never actually hit that number, but we get really close. And this is how they work. So we have like these functions, and if I plug in 100, I get 100 squared plus 3 times 100 plus 5, which gives me 10,000 plus 300 plus 5. So 10,305. And then we have the next one. Okay, so if we plugged in 1,000, we'd have 1,000 squared plus 3 times 1,000. Excuse me, plus 5. And that would give me 1,003,005. And if I plug in 90,000, I would get 8,100,270,005. And if I plug in 900,000, I get a number that is greater than 8 times 10 to the 11th. So that's an 8 with 11 zeros after it. And it's bigger than that because it has these other digits in there and a 5 at the end. And if you plug in 8 million, you get a number that is greater than 6 times 10 to the 13th, which is 13 zeros. And if we keep going, you can see this just keeps getting larger and larger and larger. What we plug in for x, as x grows, the function grows. And it's never going to hit a limit. If I keep plugging in bigger numbers, it's just going to keep getting bigger and bigger and bigger and bigger. It's just going to grow forever. So we have no limit on this type of function. So this is not one of those examples, like I was telling you, where you can have a number that it gets close to. This doesn't get close to anything except infinity itself, which is not a number, as we discussed. Okay, so if you were to write this, when we write about a limit, okay, we write the limit of f of x as x approaches infinity. Lim, it says lim when we are doing it, when you write it out mathematically, but this stands for the limit. So you would read this as the limit of f of x as x approaches infinity. Okay, that's what this says. Well, there is no limit. It just keeps getting bigger and bigger and bigger and bigger. So when that happens, you say that your limit is infinity. Because that's what's going to happen. It's just going to be approaching infinity. Does that make sense? On this one, if I plug in 100. Okay, so we have, do you guys have the function on your paper? It seemed to have disappeared off my notes. Okay, it's on my paper, but it's not here. I don't know what happened to it. Okay, this is my function. Okay, so 6x minus 1 divided by 3x plus 2. Okay, and what happens if I plug in 100? I have 6 times 100 minus 1 divided by 3 times 100 plus 2. So that's 599 divided by 302. And when you get that, you get this nice long, hold on, let me write it down. 983443709, and it continues. And then if we do 1,000, we get the same setup except with 1,000s in it. So that's 5,999 divided by 3,002. And you get 1.998334444 forever. And then if I plug in 90,000, Bless you. And if I plug in 900,000, and 8 million, yeah.
But with all of the numbers behind it, it is
Yeah.
for sure.
But what number is this getting close to? 2.
Right.
And it's, as I start out really close to 2 already when I put in the 100.
Right.
And then as I hit bigger numbers, I just get more 9s in the decimal. So I just get closer and closer and closer and closer and closer to 2. And I plugged in 2 billion here. And I still didn't hit 2. If I plugged in 5 billion, I would just get more 9s down the list. And I'm just going to keep getting more and more 9s before I start getting other numbers. But I'm never going to actually ever hit 2. Because the fact that this is a -1 and this is a +2 makes this odd and this even. So it will never divide evenly as a 2. Does that make sense?
It almost sounds sad.
Yeah, but it's just getting close. But since we're getting close to 2, but we're never actually hitting 2, that's when we can use a limit. So we have the limit of f of x as x approaches infinity. So as x gets bigger and bigger and bigger and bigger, this gets closer and closer and closer to 2. And it gets so close to 2 that it might as well be 2. So if we're given the function 2 to the x, we want to find the limit of f of x as x approaches infinity. So if you were given a problem like this, so for example, an extra credit problem on the test, just hypothetically, what you want to do is you want to make an x and f of x table. And you want to pick some value for x. So if I pick 100, actually I'm going to go with 10. I'm going to start even smaller because this is like a really big number. So f of x will be 2 to the 10th. Which, I didn't actually memorize that one. I have quite a few of these memorized, but I don't have that one memorized. Okay, so that one's 1024. And if I put in 100, I'll have 2 to the 100th. And that is 1.267 times 10 to the 30th. So this is a 30-digit number, well, 31-digit number. And if I go to 1,000 and I put in 2 to the 1,000th, my calculator says overflow error, which means that this number is too big for my calculator to deal with. So, too big for calculator. This is something that a computer, like a nice beefy computer, not like a little handheld pocket computer, but like a real computer would have to calculate out. And then probably not the HP I have at home, but you know, like a computer that is meant for calculations like this. So as you can tell, this is getting huge, right? So the limit will be infinity because we don't have a limit. It's just going to keep getting bigger. Okay, so 1 to the x. Now 2 to the x got giant. But that was 2 times 2 times 2 times 2 times 2, however many we said. But what happens when you multiply 1 times 1? And if you multiply by 1 50 more times, it'll always be 1, right?
It'll be what it's going to be.
Yeah. So as x approaches infinity, the limit will be 1. Now, if I put 1 over x, so I'm dividing by x. 1 over 1 would be 1. 1 over 2 is a half. 1 over 10 is a tenth. If I go to 1,000, I'd have 1 over 1,000. 1 over 10,000. 1 over 100 million. And what's happening to that fraction? As the denominator gets bigger, it's getting smaller and smaller and smaller. This is like that picture I showed you guys. So it's going to get really close to, it'll never actually be 0, because it'll be like 1 over a Google. Do you guys know what a Google is? It's a 1 with 100 zeros, right? So it could be a 1 over a Google, but it's still not going to be 0, but it gets really close to 0. Now, this one is interesting. Actually, that shouldn't be there. Cross it out. Oh, no, yes, it should. I'm sorry. Uncross it out. Sorry. As this one, 1 to the x is 1, right? Yeah. And then 1 over x is 0. So this limit kind of approaches, no, I was right, there is no x here. Yeah, it approaches 1, because this is 1 plus 0, essentially. Yeah, leave that x off. Yeah, leave that x off. Sorry, I wish I could say it's Monday. It's not Monday, is it? It's Tuesday. Darn. Yeah, it's still kind of Monday-ish. It's Monday plus 24. But so this is a 1, and this is like a 0, but it's not actually a 0. But the limit approaches 1, because it's like 1 plus, might as well be a 0. Does that make sense?
What if x is like a different number?
Well, what'll happen if you were to graph this, right? You'd start with x being 1, so you'd have 1, 1.
Pretty much like a
And then you go down and down and down and down and down. But except you go down to, sorry, you'd start over, you'd have 1 plus 1, so you'd start at 2, and then you'd go down to 1. And then it goes, that fraction keeps going down, but it pretty much stays close to 1 at that point. Does that make sense?
Yeah.
Okay. Now, that means that it's greater than 1, because it's 1 plus whatever that minuscule fraction is. So it's greater than 1. But if we raise it to the power of x, it's not going to get bigger than 1, because this is close to 0. So that's kind of like the 1 to the x thing. So you're kind of combining this. And so it's kind of having like this freaky battle, because it wants to be a 1, but it's not a 1, because this is greater than 1. But it's not that much greater than 1, and it's going close to 1, and so it sort of freaks out, and you get this thing happening. You get a 2.7 something. And the limit of 1 plus 1 over x to the x, as x approaches infinity, approaches a very, very special number in math. E. E. E is the base of the natural logarithms. It's the exponential base. That's what it's called, the exponential base.
So how do you get from
And it's about 2.718. It's like pi, though. We're rounding. You know, we call pi 3.14, but it's not really 3.14. We call E 2.718, but it keeps going.
how did you get to 2? I thought it was supposed to stay 1.
That's what I'm saying. It has this weird battle happening because of the fact that this is actually greater than 1. It's not 1. So if we go back just for a second, this 1 to the x is 1. And 1 over x approaches 0, but it's never actually 0. So I'm adding 1 plus a little bit more than 1. Or, I'm sorry, a little bit more than 0. So I'm adding like 1 point, 100 zeros, and then a 5 or something. You know, it's not quite 1. And then I raise that to a high power. Well, because it's not a 1, it has a 1 with a decimal, and I raise it to a high power, it wants to go big. But because of this happening here, it brings it back small. But we're adding 1 to it.
So then it would be 1
plus 1 point, yeah.
But that's what I'm saying. When you
So here's
those are 2 points of the function.
here's what's happening.
So how did you get a whole other 1?
Well, here's what's happening. This x out here being an exponent, being that this is greater than 1, like our 2, how it went huge, this x out here is wanting to bring this whole thing giant. Like just infinite. But this x inside here, which is also getting, these are the same x. So if this is a million, this is also a million. So this x in here is trying to pull it down and make it minuscule. So 1x is trying to make it giant infinity. 1x is trying to make it itty bitty smaller than anything and pull it down. And so they're pulling in opposite directions. And that happens to bounce it into the 2.7 range. Does that make sense? It's okay.
I was just thinking like 1 times itself a bunch of times doesn't make it more than 1, but
because of this, yeah. It's like it's pulling it in 2 different directions. In one direction it wants to go giant, and in the other direction it wants to go like infinitely small. And that pulling it in other opposite directions happens to land it in a very special place. Which e, the exponential base, is not derived from this limit. It's just that this limit happened to hit there. And that's one of those kind of freaky coincidences that happen in math. And does this look familiar at all to what we did yesterday? 1 plus r over n to the nt. It looks like the compound interest formula. And that's where things get even more interesting.
oh no.
So e is the exponential base, and it's about 2.718. It, has longer decimal string, but we round it.
What is exponent?
What we have you heard of logarithms? You have logarithms, and you have like different bases of logs. There's like log base 10, which is the one we use most often because we're in a base 10 number system. Well, then there's something called the natural log. And e is the base of the natural logarithms. And the way logs work is that an exponential function is when you have the variable as your exponent. Logs undo those. So a log and an exponential are opposite the way multiplication and division would be opposite, or squares and square roots would be opposite. But since it's the exponent that's the variable, or the variable that's the exponent, you need a special function to undo that. And e is the one that undoes, e is the base. So e to the x is the exponential, and e is the base. And so if I take the natural log of e to the x, I get e, because the natural log and they undo each other. Does that make sense, kind of ish? That you get more into in like higher math, logs and natural logs and stuff.
I have a question. Say we were doing a problem that you had to have a variable or something for this type of problem. Would we round it, or would we just mark that as e?
If you got to this, you would just go ahead and put in e. And if, like, let's say some limit gave us 3.14 or something, you would just go ahead and say pi. If you recognized it as a special number. If not, then you would say 2 or 3 almost. What's the question?
So when you make that exponential base like down 2.718 and it starts at 2.7, it's going to end at
Yeah, but see here it's going 2.718, and as we keep going, it's just these numbers that change, and it stays 2.718, and then other numbers.
Okay.
So it gets really close to that. Okay, so we call that E. We already did that. Okay, so here's what happens. If we deposit $1,000 at 100% interest, compounded continuously. Okay, here's what continuous compounding is. We've talked about annual compounding, that's once a year, semi-annual is twice a year, daily is every day. Continuous is every second, every microsecond. It's constant. It's constantly calculating. It never stops. Calculations run into calculations, run into calculations, faster than we could possibly do them. The computers are doing these calculations. Nanoseconds. Okay? Infinite calculations in a year. Yeah. Yeah, Aiton.
You said this, I'm not Catholic at all, but you said something about math being different.
So continuous, you have infinite compounding, right? So in a 1-year period, you're talking about compounding parts of seconds, every parts of seconds, so it's infinite. So if we put this in here, what would happen is we would get a rate of 1%, or rate of 100 gives us a 1, right? Our number of times compounded would go to infinity. So if this was nt, and this is n, we'd have that infinity happening. Well, here's this. We looked at this already. This part right here, we found goes to E. Right? In our calculations. So this is the same thing as 1,000 times E, which will give us about $2,718.28. Now that's only if we have a rate of 100% and over 1 year. E is a button on this one, but not every calculator has an E button. So E is approximately, huh? No, that's not it. It's lowercase e. This, like this, the capital E's, is the same thing as times 10 to the whatever the exponent is.
So what I'm trying to figure out is I look at a calculation that says infinity without calculation.
That's where we're getting there.
Okay.
Yeah, we're going to get there. So that double E, capital double E, is the same thing as scientific notation. You're looking for a lowercase e. If you can't find it, though, you just plug in 2.718.
So E is 2.718?
It's approximately, I'm rounding.
What is capital E?
This double E thing is scientific notation where you can do like 1.2 times 10 to the 10th. So you'd put in 1.2, hit that button, and then you'd hit in the exponent.
So is E always going to be 2.718?
Yes. It's a constant like pi. Yeah, it's always, it's a special number. It's always that number. It's constant. Too hard when we had an interest rate of 100% and we were talking about 1 year. That worked out fine, right? That's like lovely, nice. But if we have an interest rate that's more realistic, not 100% interest, because hey, if you guys ever find a bank that pays 100% interest, you call me. I need to know about that. Okay? But what happens? Yeah, exactly.
Is that every day or every time?
Every time it's compounded.
Is 4.3 good?
4.3 is higher than anywhere you'd get right now. Yeah.
It sounds good.
Okay, except this is x times 5. So infinity times 5. But okay, what do I do with this? I have to divide 0.043 by infinity and then raise it to the power of infinity times 5 and then multiply it by 1,000. I can't really do that. But this gives us that last problem we did where we ended up multiplying by e. It gives us the continuous compounding formula. I'm losing my handwriting again. Which is B equals P-E-R-T. PERT. So it's P principal times E raised to the rate times time.
Is that how PERT?
No, that's practice, entrance, something. I don't remember what that is. Yes, it would. Okay, P is our principal. E is 2.718. R is the rate as a decimal. And T is the number of years. So I can solve this using this formula. I don't know what to do with that. I can't, on a normal calculator, with a calculus calculator like a TI-92 or something, I could plug that in and I would get an answer absolutely all day. Here, oh, that's a B. Balance, sorry. But on my normal TI or a normal scientific calculator, I can't do anything with this. But this I can. My principal is 1,000. E. My rate is 0.043 and my time is 5 years. So if I multiply 0.043 times 5, I'm going to get 1,000 times 2.718 to the 2.215. So I'm going to plug in 2.718 to the 0.215. And I'm going to get 1,000 times 1.2398, etc. So I'm going to multiply that by 1,000. I don't cut it off. What I do is when I do my calculations, so I did the 0.043 times 5, and that was all the decimal it gave me. Then I did 2.718, and I raised it to that power, and it gave me that long string of decimal. And then I just left it in there and put times 1,000. Yeah. And so at the end of that 5 years, I'll have $1,239.83 with continuous compounding. Just to compare. With normal compounding, let's just do simple interest. So 1,000 times 0.043 times 5. So with simple interest, I'd have 1215. With continuous compounding, these are infinite calculations. I get an extra, what is that, 2483 over 5 years. And that's what's kind of funny, because you'd think continuous compounding would, you're talking infinite calculations, you'd think, wow, this is going to be a huge amount of money, right? Except they're infinite calculations that are giving you fractions of a penny every time. And so the next calculation only has a fraction of a penny higher, and so it takes a long time for those things to add up, because you're talking about fractions of pennies. But, yeah. But you did get an extra $24 out of it. So, if you can find continuous compounding bank account, go for it.